Hello dear friends, in the previous class we have studied about designing of analog filters. In today's class we will be discussing how to design digital filters. To design the digital filters there are two methods, bilinear transformation and impulse invariant response. In this video we will be discussing bilinear transformation. The numerical given is design a low pass filter that is required to meet a following specification, which has monotonic passband and stopband, minus 3.01 dB cutoff frequency of 0.5 pi radian, stopband attenuation of 15 dB at 0.75 pi radians. Find resistor function h of z and the differential equation realization. Use bilinear transformation. When we see the term monotonic, it is Butterworth filter. This is Kp, this is Ks, this is omega p and omega s. This is in bilinear transformation we have to do the pre-warping step. For pre-warping we have to find omega p dash, which is given by 2 by t tan wp by 2. Wp given is 0.5 pi. When we substitute this in the formula we get 2 radian per second. Similarly, omega s dash is equal to 2 by t tan ws by 2. Ws is given as 0.75 pi. Hence by substituting it in the formula we get 4.828 radian per second. The given value 3.01 dB is Kp, omega p dash is 2 radian per second, Ks is 15 dB, omega s dash is 4.828 radian per second. Substituting this in the formula to find the order of the filter n is equal to log 10 raised to minus Kp by 10 minus 1 divided by 10 raised to minus Ks by 10 minus 1 whole divided by 2 log omega p by omega s. Substituting this in the formula we get n is equal to minus 1.9416. Rounding off it to the next integer, we get n is equal to 2. Now we have to find the cutoff frequency omega c. Omega c is given by omega p dash divided by 10 raised to minus kp by 10 minus 1 whole raised to 1 by 2n. Substituting the values of omega p, kp and n in this formula, we get omega c is equal to 2 radian per second. For n is equal to 2, we know the Butterworth polynomial s square plus root 2s plus 1. Inverse of the Butterworth polynomial gives us the transfer function for order 2. Therefore, h of s is equal to 1 divided by s square plus root 2s plus 1. Since we are asked to design a low pass filter, we have to apply low pass to low pass transformation. For applying low pass to low pass transformation, we have to substitute s as s by 2. Since omega c is 2, we are substituting s by 2. Substituting s by 2 in this in the place of s, we get s square by 4 root 2 into s by 2 and 1 as it is. Taking the LCM as 4, we get h of s is equal to 4 divided by s square plus 2 root 2 s plus 4. The steps till obtaining the transfer function is same for analog and digital filters. For bilinear transformation, the formula is h2 of s is equal to h2 of s at s is equal to 2 by t 1 minus z inverse divided by 1 plus z inverse. Substituting s as this term bilinear transformation, we get the digital filters. Since it is s square, 2 by t is 1 second, 2 by 1 into 1 minus z inverse divided by 1 plus z inverse whole power 2. Since this is s square plus 2.828 s it is, in place of s we are substituting again this term plus 4. After taking the LCM, we get 4 into 1 minus 2 z inverse plus z power minus 2 divided by 1 plus z inverse whole square plus 5.6568 into 1 minus z inverse divided by 1 plus z inverse plus 4. After taking the LCM and sending it to the numerator, the steps are written as below. We obtain the transfer function h of z is equal to 1 plus z power minus 2 whole square divided by 3.4142 plus 0.5858 z power minus 2. Substituting z is equal to e power j omega in place of z and applying a plus b whole square formula, we get this as below. Substituting e power minus j omega as cos omega minus j sin omega and e power j 2 omega as cos 2 omega minus j sin 2 omega, and solving it and evaluating h of e power j omega at omega is equal to 0.5 pi radian, we get 1 plus 2 into cos pi is 0 minus j sin pi minus j, and similarly substituting all the values we get the transfer function, and the 20 log of this transfer function is minus 3.01 dB. Similarly, evaluating this transfer function at omega is equal to 0.75 pi, and solving it and taking the 20 log of that answer, we get minus 15.43 dB. In the question, we are asked to find the register function h of z and differential equation realization. Now we have found the register function h of z. To find the differential equation realization, we know that h of z is equal to y of z divided by x of z. We have previously obtained the h of z as 1 plus 2 z inverse plus z power minus 2 divided by 3.4142 plus 0.5858 z power minus 2. The numerator is the y of z and denominator is x of z. Cross multiplying this, we get 3.4142 y of z plus 0.5858 y of z into z power minus 2 plus x of z plus 2 x of z z inverse plus x of z into z power minus 2. Wherever y of z is there, it is y of n. Y of z into z power minus 2 is y of n minus 2. X of z is x of n. X of z into z inverse is x of n minus 1. X of z into z power minus 2 is x of n minus 2. We want to obtain y of n. Hence, keeping the y of n and in the LHS and sending other things to the RHS, we get y of n is equal to 0.29289 x of n plus 0.58578 x of n minus 1 plus 0.2928 x of n minus 2 minus 0.01472 y of n minus 2.